One possibility is decay of radioactive isotopes, which we saw heated the interior of the Earth for billions of years. We don't think that there's much in the way of heavy, unstable radioactive isotopes at Jupiter's distance from the Sun, basically because of the same idea I've been saying about solar system-wide differentiation. Okay, the radioactively unstable isotopes tend to be things like uranium. Now, if you remember your periodic table, uranium is much heavier than iron. It's a heavy guy, right? So it would tend to be clustered near the Sun. So you're not going to get much uranium out of Jupiter's distance. So you're not going to get much decay. So that's not the energy source that powers this higher temperature we're talking about now. Another possibility is that Jupiter is actually still in the process of squeezing down. Its own gravity is possibly still squeezing it down to have a smaller radius. Now, when you do that, if you take a planet and allow it to collapse under its own gravity, that squeezing actually does lead to heating. And you probably realize that when you squeeze something, you heat it up. It's almost like a frictional thing in a way. Well, we think that that actually is what's going on in this case, that the leftover heat that's still propagating out of Jupiter from the squeezing that took place when it collapsed, which we call this heat of formation, is simply still leaking out through the atmosphere. So what that means is that eventually, maybe in another billion years or so, Jupiter will reach that temperature of 105 degrees at the cloud top, the expected equilibrium. It just isn't there yet because it's still cooling from this period when it was still squeezing down to become as compact as it is now. All right, so we see when we look at Jupiter complex patterns of atmospheric bands. We also see storms. We see evidence for what we call shear flow, which I'll explain in a minute. It's actually that these bands that we see are moving relative to each other, like separate wheels. We also, of course, see the Great Red Spot, which is a single storm larger than Earth that's lasted for hundreds of years. Now, it's been a long-standing mystery how you explain the motions that we actually see when we look at, the motions of the clouds and the storms that we see when we look at Jupiter. We think it can be explained by a combination of the solar heating at that distance from the Sun. There's still some solar heating. Jupiter is 3-degree tilt. It's a pretty small tilt of its spin axis. And the heat of formation escaping from the interior, creating vertical convection, we think probably can explain what's going on. But it's kind of complicated. It's more complicated than what we see when we look at Earth. Because Earth just has this thin atmospheric layer, Earth is, 4,000 miles in radius, but the atmosphere is only maybe 30 miles thick. So the atmosphere is a tiny, tiny layer compared to Earth's radius. On Jupiter, it's completely opposite because the whole planet is atmosphere. So when we look at Jupiter, we have to consider much more of a three-dimensional kind of flow, much more three-dimensional in the vertical direction. So what we find is there are convection patterns, vertical convection patterns, because we have warm material rising, cool material sinking. Now notice that when material comes up here, it's changing its latitude a little bit, because these bands run parallel to the equator. So when material comes up, it's arcing a little, and that arcing is changing its distance from the equator. And you remember that just on Earth, the same thing happens on Earth. When material changes its distance from the equator, you get that Coriolis force, because of the fact that the gas is not matching the actual local speed of rotation of the planet when it changes latitude. It's moving a little too fast, a little too slow. That tends to generate the belt motions. The excess Coriolis effect generates the belt motions, and then chemical processes tend to divide it into these bands. So we see very complex behavior. It's actually a chemical reactor, really, on Jupiter. All kinds of interesting chemistry is going on all the time, driven by a number of different processes. There's an actual flow of different streams of material, like you have in a chemical factory. You have flows of different streams of material with different properties that come together. That can happen in regions of different properties, meaning different temperatures and densities. And then on top of that, you have the vertical heating circulation I was talking about. So you have all the ingredients for an actual, very sophisticated, complicated chemical factor going on there. And this also is connected with storms that we see, because the storms are driven by this kind of mismatched pattern of the bands. And this is what we call shear flow. So shear flow means that you can have one band moving one direction, another band moving the opposite direction, and they can actually wind up a storm type of pattern like that between them. And there can be a lot of evolution of these little regions here. You can see evolution of this on a weekly basis if you look at Jupiter close enough. It's not a static situation at all. All these little plumes and things are evolving on a daily and weekly basis on Jupiter. Okay, so to go into the interior, the atmosphere is very, very extensive. So its radius at 71,000 kilometers is about 10 or 11 times larger than Earth. Okay, so we already said that Jupiter is 318 times the mass of the Earth. It's also much bigger in radius than Earth, about 11 times larger than Earth. And what we find is the atmospheric layer in the outer region is mostly the very outer region, the outermost 100 kilometers, is molecular hydrogen H2, just like we've been talking about. So when I showed you that cutaway of the atmosphere, we were just seeing regular molecular hydrogen H2. But if you go down to a deeper layer than what we saw in that temperature diagram I showed you, you reach such a depth that the pressure is so high that the molecular hydrogen can get squeezed into a new phase of hydrogen called metallic hydrogen under great pressure. And so this is going to exist below a radius of about 50,000 kilometers, which is a few thousand kilometers below the outer actual radius. Much farther in, we do see a rocky core with a radius of about 10,000 kilometers. And remember, Earth's radius is about 6,000 kilometers. So this rocky core is a bit larger than Earth. And even though we call it a rocky core, it's probably not something we would recognize as a rock, because at that depth, the pressures and temperatures are so high that it's really molten rock. It's more like you more think of it as kind of a magma core or something like that. The temperature at the dead center around 40,000 kelvins, and a pressure of about 50 million bars, which is 50 million times Earth's pressure. Okay, so I'm not going to go too much further today, but I just want to point out that a lot of people look at Jupiter and actually call it a failed star, because these central conditions are pretty darn extreme. 40,000 kelvins and 50 million times Earth's pressure. They're moving in the direction of conditions that are so extreme you could have nuclear fusion, which is what we have in the core of the sun. They're actually not extreme enough to do that, but they're moving in that direction. So, if you could dump more matter on Jupiter, actually you have to dump quite a lot more matter on Jupiter, but if you did that, you'd make the conditions in the center even more extreme, and you would actually be able to start nuclear fusion and have a star there. So, okay, I think I'll end that there. We'll pick it up back on Thursday.